Yes, I'm Lee Spector. I'm a professor of computer science at Hampshire College in Amherst, Massachusetts. I like to define artificial intelligence as a human activity. And in that context, I define it as thinking about thinking by programming. So the idea is that if we want to understand what human thinking is and what intelligent behavior is, there are many ways to do that. And as a cognitive scientist, I'm interested in pursuing many of those. But when we pursue those questions by writing code, that is what I consider artificial intelligence to be. And doing that allows us, or actually forces us, to be very explicit in what our theories are and what the details of it are, and to learn by experiment with these computational systems what those theories imply and whether or not they match thinking as we observe it in other ways. Well, what really got me excited was that in an evolutionary computation system, you can set up an environment in which intelligence emerges, and in which one has to put in relatively little theory in advance, because the evolutionary process can develop intelligence in ways that you didn't predict, that you didn't design in advance. So I got most excited when I read John Koza's 1992 book on genetic programming, where the idea is that if there is a computer program, any computer program that could do the thing that you're interested in it, then conceivably evolution could find that program without you really having any idea in advance what it would look like. And so it allows us to become experimentalists who create initial conditions, a primordial ooze and a problem environment, and then we let the power of random variation and selection operate, and out of that often emerges intelligence, creativity, leveraging the power of random variation and selection that's produced everything around us in terms of natural evolution. So that's one of the joys of working in evolutionary computing, is that quite frequently you set up this primordial ooze and you set up the selection process and the variation process, and you do that in a very general way, and then you sit back and evolution takes place, and quite frequently you're surprised by what emerges. One instance that was meaningful to me personally is I've done some work in the evolution of quantum algorithms, where we evolve algorithms for quantum computers. And this is a particularly exciting application area because it's quite difficult for humans to program quantum computers. They're counterintuitive in many ways, to put it mildly. But evolution doesn't have a problem operating in that space. And I had set up an experiment where I was trying to evolve a quantum algorithm for a certain problem. And it found something that I thought was completely novel and a breakthrough in quantum computing. In this case, it was not. It was actually something that, had I known my quantum physics a little better, I would have known could be done. But it was news to me. As the experimenter, I had no idea how to design a system that would do that thing, or that it was even possible, but evolution found the way to do it. And that convinced me early on that genetic programming could find quantum algorithms that were beyond my ability to find, and indeed it turned out that it can find algorithms that were beyond the ability of any humans to find. And so we ended up having new results emerge from our genetic programming system, which were publishable as results in the physics literature, which evolution found. We did not find the evolutionary process found. So that was very exciting. Well, one of the key questions in the design of a genetic programming system is, what is the language in which the evolving programs will be expressed? And it turns out that matters a lot. Ideally, you want a language that can express everything that you would like your programs to be able to do, but is also compatible with the evolutionary process, so with random variation. And most programming languages are designed for human programmers. They're not designed for random variation. So we've designed a programming language called Push, which was designed from the ground up as a medium for evolved programs rather than human-written programs. And this has a number of advantages over previous systems. So that's one area in which I've done work. Another one that I'm quite excited about relates to the ways in which programs are selected to be parents of new baby programs in the evolutionary process. In most prior genetic programming work, we evaluate each program and give it some sort of numerical grade for how good it is. And then we use those grades to select, well, who deserves to have babies. That, along with many other aspects of our evolutionary processes, is a real caricature of what happens in biological situations. And this is one area where we felt it was too much of a caricature, that it's holding us back. In real life, you're not judged by one number that determines how many offspring you're going to have. Rather, you face a sequence of challenges over your life, and the ways in which you handle them either do or don't get you to the point where you have offspring. It's true of all life forms. So we developed a new parent selection method called lexicase selection, which takes every challenge that you might have as a sort of independent test, and programs are subjected to these in random sequences. And this produces much more diverse populations, each member of which might specialize in different abilities, and yet selects parents that are good at certain things and good at certain combinations of things. And this has produced much better results in certain areas of genetic programming. And so I'm very excited about where that's going to lead. Certainly, it is now being applied in several commercial settings. In particular, genetic programming is quite good at finding formulae that characterize data, doing prediction, doing classification. I'm more excited about future commercial applications where the system discovers a new program that might be the kind of program that a human would write, involving multiple data types and complex control structures, and yet a program that does things that no human has ever figured out how to do or that even needed to be done. So this idea of automatic programming more broadly, where you state what you want a program to do in some very general high-level terms, and evolution figures out how to get a program to do it. One could imagine something like an app store where instead of picking from already written programs that were written by humans, you specified the kind of program that you wanted, what you wanted it to do, and it automatically programmed it, right? There are many ideas for how automatic programming could be so robust, but I think that evolution will probably be an important part of the mix for the most powerful automatic programming systems. Well, evolution and learning are at a certain level of remove similar processes. You could think of an evolutionary process as a learning process. When we think about them in biology, they're at very different scales, right? Learning happens within an organism over its lifetime. and evolution happens over many generations within a population. So the key ideas are quite different, and I think they will have different applications in technology moving forward. Deep learning is a technology driven mostly by ideas from how learning happens in brains over an individual's lifetime. And that allows it to be very powerful within certain constraints. Evolution is a more open-ended process that produces everything from mushrooms to humans, and mosquitoes and all of these different life forms that have very different designs, and solve different kinds of problems. And I think that the evolutionary ideas will be important in machine learning, in technology, and AI for problems at a larger scale, requiring different sorts of creativity and different kinds of innovation than deep learning is situated to solve. I think that the future of AI is going to involve ideas from neuroscience and things that are currently in deep learning technology, and things from evolutionary biology, and things that we are playing with in evolutionary computation. These things, I think, will all play a role in the future of intelligent technology. And the exact way they'll go together, I don't think anybody yet knows. But I think that they all offer important insights. Absolutely. I think that there are various ways right now that people are combining ideas from evolutionary computing and deep learning. Um, and I think that that will continue to be important. Um, they, they can solve different aspects of a problem, and they can give us different insights into how to build intelligent systems. Democratizing AI. AI is a very powerful technology that brings into pretty much anybody's hands um, great capabilities. In a sense, it is sort of self-democratizing in that it's the ideas that are powerful. And as long as you have access to the ideas and computer power, um, you can do quite a lot with it. Um, so I don't know if the most important question is how we can democratize it. I think it's important that we figure out how to teach it well. But I also think it's really important that we figure out how to protect ourselves from it and to understand the impacts that this powerful technology is having already and will continue to have on our societies. I think that there are already many previously unanticipated consequences, social consequences to AI technology, that many people in the field have anticipated for many years. And only within the last few years has that really begun to sink into the broader society. Um, what it's going to take to live symbiotically with our technologies, um, I don't think we fully understand. I don't think anybody understands that. I think it's really important that we have active discussions about not only bringing the technology to more people, which is, I think, what you implied by democratizing it, but also how does society manage itself um, once intelligent technology is pervasive, which we are on the cusp of. Our societies are beginning to have pervasive AI embedded within them, and we are just beginning to understand the many ways in which that can affect our future. Well, One way to think about this is that everything we care about is a product of evolution. We are products of evolution. Our societies are products of evolution. The built environment, our science, our art, everything is a product of evolution. The evolutionary process is beginning to operate also in our technological artifacts, in part through our intellectual activity and our building of computers and our designing of evolutionary algorithms. I think that there is a sort of merging of all of the concerns of human society with the products of our technologies, and that it's going to be hard to draw the lines and say, oh, this is an application of evolutionary computing a few years in the future. And so I think you have to be a general futurist about this, which I'm not really a futurist, but you would have to say, where is humanity going? And evolutionary computing and AI in general are going to be part of where humanity is going, with all the excitement and all the perils that implies.